For all those who are joining me for this video, I hope everyone's having a great evening. I am Mr. Ish. Thank you for joining me. We're looking here at the quick proof of the power function derivative. Not very many people are familiar with this term power function. Even I wasn't not too long ago, because I would always call it an exponential function having a different base, but anything which looks like b to the x is generally called a power function. You know the derivative of this because we've done derivative videos is always equal to bx ln b. We know this. We've seen this before and we've used these type of questions here for derivative videos in the past. What we want to do is show why this is the case. Why does this power function lead to that in terms of its derivative? You could very graphically do it easy. You know b to the x is very similar in terms of graph to the e to the x, always going through 0, 1. If you were to do at various points a tangent line, you know you'd see tangent lines all with positive slopes of a varying degree of steepness or flatness. If you were to plot these x points, these x-axis values with the slopes of the tangent lines that were generated by those x-axis values, you would get a curve which would look very much like this, altered only by this little factor which comes into play, but it would look very much like a power function. But that right there is not the purpose of this video, because we don't want to do graphic derivation of this. However, you can look at a very easy way this way. If y is equal to b to the x, if b to the x is the function that is being hit by the derivative and y is equal to b to the x, you can use the properties of natural logs. Ln y is equal to x ln b. You can do implicit differentiation. If you were to implicitly derive this, you'll have d over dy ln y dy over dx, which is the factor you would solve for, is equal to ln b, a coefficient that has been pushed outside of your derivative. You would get here in terms of ln y, it become 1 over y. You know, with respect to dy over dx is equal to just ln b, because the derivative of x is just a 1. You would solve for this dy over dx by pushing this y onto the other side. You'd get y ln b. When you resubstitute this y, which was originally equal to this, you'll get dy over dx, which is the derivative with respect to y, is equal to b to the x ln b. And this is something you can remember, because that shows you in an informal manner why this leads to this in terms of a derivative. But this entire procedure here should be kept into mind, because when we look at the formal proof of this assumption, if you want to call it, will very much come into play, because when we need it, we can utilize this to bail us out over there. The formal proof, as you can imagine, will depend on the limit technique. And then let's begin that procedure. If f of x is equal to b to the x and we're trying to determine and prove the derivative of that, we will utilize that basic definition of a derivative, which is very well dependent on this limit technique. Everything will fall into that with respect to that. You'll have b into x plus h minus b to the x over h. You know we have a limit here sitting outside as h approaches 0. Very easily, just like the exponential, b to the x plus h came from two items which are multiplying, each having a different exponent but the same base. Using the properties of exponents, this can be thought of as that. And exactly that's how we should proceed. You will have b to the x, b to the h minus b to the x all over h. You see, this has kind of played in the past with the exponential function derivative, but again, formally you should know how to derive this power function derivative, and that's what we're doing here. Isolate a common term, which is b to the x. Limit h approaching 0, we have b to the x, and then within that we have b to the h minus 1 all over h. We can even isolate the h under this part right here. You can separate that using the properties of limits. The limit of a product is equal to the individual product of the separate limits that are involved. Limit h approaching 0, we have b to the x, times limit as h approaches 0, we have b to the h minus 1. This is the area where I need to be bailed out. Why? Because I have b to the h minus 1 over h. If I were to put 0 in places of these h, what will I get? I'll get 1 minus 1 over 0. I'll get 0 over 0, an indeterminate limit form for which you can use the L'Hopital's rule procedure to evaluate this part. When you would evaluate it, you do the derivative of the numerator and derivative of the denominator with respect to the h. But we've already looked at that earlier derivation procedure for anything which looks like b to the x or b to the h. It doesn't matter what the variable, but anything which looks like a power function. We've evaluated that. In terms of this numerator and in terms of this L'Hopital's rule procedure, the numerator derivative would become b to the h, ln b, minus 1 is just a 0. This will become a 1, and you can literally put 0 in places of h. When you put 0 in places of h, this becomes a 1. You're only left with ln b. This is the end result of that part right there. So we're looking at limit h approaching 0, b to the x, which is just b to the x. H approaching 0 does not affect that. We have ln b coming out from over here, ln b. You combine these, you have b to the x, ln b, and the proof is done in terms of the derivative having been derived. When you are deriving the derivative and utilizing this procedure, this right here is your proof for this power function derivative, because you're proving and you're showing this to be the case. And with that, let's say adios to everyone watching this video, and I appreciate everyone who has been watching my videos. Questions, concerns, or comments, let me know, or any ideas you want for videos, let me know. Thank you. Have a nice day.